Yeah, real brief. It kind of applies to everything we did today because these were meta-analyses. Just as a general rule, if we can, I'd like to see us start defining some of the statistical terms just at the beginning of Journal Club. Some of us are familiar with it, some of us are not. The difference between odds ratios, relative risk, absolute risk reduction, number needed to treat, number needed to harm, stuff that you kind of see and stuff that you're utilizing in practice. If we can just define those at the beginning of each thing, I think that'll help reinforce that stuff as we go along. Real quick, a meta-analysis was briefly introduced by Dan McCollum at the beginning. Typically what we've seen today is there's been some kind of study selection criteria, literature search that has had certain things that are being looked for to evaluate. Those RCTs are then kind of pared down, and then the data is kind of aggregated and mashed together. In a meta-analysis, you're always going to have some degree of heterogeneity probably because however many of your studies aren't going to be the exact same studies. So that's why, again, kind of like we talked about and kind of the point LaShawn made, in some of the papers, or rather in the very first Journal Club, in some of those papers, when you say that there's zero heterogeneity for a meta-analysis, you got to be a little bit skeptical of that. And kind of the point Dan McCollum made, garbage in, garbage out. If you take a bunch of crappy papers and try to aggregate the data, you're still going to get crap on the back end. Heterogeneity is the problem when you try to aggregate data that can be slightly different. That's the statistical word. The way that authors, statisticians try to adjust for heterogeneity is something called random or fixed effects models. So a fixed effect model is a statistical model that tries to correct for a sampling error and assumes that there's not some outside variable that's causing the heterogeneity in the trial. It's just the way that the sample was drawn. It's a statistical problem, not a larger problem with multiple variables. Most of what we look at in medicine isn't a fixed effect model. It's a random effects model. There's co-founders outside of the paper itself and the statistics themselves that are leading to the heterogeneity. Does that make sense? So random effects model is classically what you see for folks trying to correct for heterogeneity. The I-squared statistic, that's come up multiple times this morning. 20 years ago, they would basically try to quantify how much heterogeneity there was between each paper in a meta-analysis and then create something with a p-value. And so p less than 0.05 would be significant, greater than would not, and there would be a ton of heterogeneity there. That was widely criticized because when you have 8 RCTs, your sample size is 8. You're not really powered to pick up a meaningful difference among 8 different studies. And so in 2003, published in the British Medical Journal, was a number of guys that had kind of gone through and created a new model for heterogeneity, I-squared. Without getting in the weeds, I-squared is measured 0 to 100%. 0% would presumably be no heterogeneity. 100% would be as much heterogeneity, completely different studies, kind of questionable to match the data together. And so that's why you see I-squared in a lot of these meta-analysis now.
Does that make sense, guys? What would it look like if you had minimum heterogeneity, meaning everything matched up exactly similar? They're not different at all. Versus max heterogeneity, which are things so diverse that you really shouldn't be comparing them at all together.
Sensitivity analysis is something that comes up a lot in these meta-analysis. Sensitivity analysis is basically, and I'll talk about this in this EVT paper, if you pull each individual study out of the analysis, how much does each individual study influence the outcome? Does that make sense? So if I analyze 7 instead of 8 RCTs in this paper, does it influence the outcome by pulling out one study? Does that one study so heavily weigh on the results that it shouldn't be used, that it just overwhelms everything else, that it has too much power to influence the results? That's what sensitivity analysis does.
An example of when that would be really important, say you got 10 studies, but one has 10 times as many patients as all the other ones combined, then you're going to have that one study dwarf everything else. And so it's a very unbalanced meta-analysis.
And you'll see typically a table that is showing the weighting. In most of these meta-analysis, you'll see a table somewhere in their figure that shows the weighting based typically on something like sample size for each of those papers and how much they're influencing the outcome of your meta-analysis.
So in the same way that you wouldn't necessarily trust a randomized controlled trial, that if one more person died in one group versus the other, then it will be enough to make the finding invalid.
Statisticals, yeah.
You'd be really questioning a meta-analysis. If you pulled one paper out of that clump of papers, does that make the entire result go away? Because ideally, if there's a true clinical effect, you would see it pretty consistently. And even if you pulled one or more of the studies out, you would see a pretty clear clinical picture that, yeah, we're all pointing towards this being a good idea or a bad idea clinically.
And then a couple things that you guys are probably familiar with, just that I'm about to talk about. Odds ratio, it's a measure of effect size, describes the strength of association between two variables. So A is exposed to this, B is not. If A has this exposure, the odds of this happening are double, triple, whatever, 2, 3. Does that make sense? And then confidence interval. Confidence intervals, your range, typically your 95% range for any value. That's what we talked about with the sensitivity and specificity for the ultrasound paper. The problem with a small sample size is that you have a huge confidence interval because, again, the paper is not powered to measure a small difference. It's only powered to measure a really big difference, so you end up with really big confidence intervals. So you can only be 95% certain that the actual true value lies within this big massive interval if the sample size is too small. If the sample size is 100,000, your confidence interval is going to be pretty narrow. You can be pretty confident that the true value lies in a pretty narrow window.